let's look now into finite, countable, and uncountable sets. Okay, so let's say we have two sets, A and B. Okay. Then a map between, let's say the map, let's call it F. Okay, between A and B is called, it's called a bijection. Okay. Two things have to happen. If F is 1-to-1 and onto. When we say onto, we mean onto B. Okay. So let's be more precise. What does it mean to be 1-to-1? This means that if f of A equals f of B, okay, then A equals B. And this has to be true for all A, B in A. Okay, and then the second, for a bijection, the other thing we need to have is that it's onto. Well, we can just say onto. Okay, this means that for each B in the destination set B, there is an element A in the initial set A such that f of A equals B. Okay. In other words, that means that for every element in B, that element is coming from some element in A. Okay. So we are going to look at what happens when we have a bijection between two sets. Okay, so we write, in that case, we write that A is equivalent to B. Okay, we say this if there exists a bijection between the two sets, a bijection F from A to B. Okay, in this case, we say that both sets A and B are equivalent. Okay, A and B are equivalent. Okay, or we also say that they have the same cardinality. They have the same cardinality. Okay. So what does this mean? So when two sets are equivalent, it's in case the sets are finite, this will mean that they have the same number of elements, but this also extends to sets that are not finite. We will get into this in more detail in a moment. Okay. So there are three properties that I want to emphasize about this equivalence relation here. Okay. So let me write that. So an equivalence relation has three properties. So the first one is that a relation is an equivalence relation if A is related to itself for any set A. Okay, this means that the identity is a bijection of A with itself. Okay. This is a bit silly, but just means that for every element in A, and you can put it in correspondence with itself by the identity. The identity means doing nothing. Okay. Then the second one is the symmetry. Okay, the first property, actually, let's give the proper name to this. This is called the reflexive property. Okay, the second property is called the symmetric property. And it says that if A is related to B, then B must be related to A. Okay. This is easy. In this case, if F is a bijection from A to B, then we can take the inverse that goes from B to A. And this is also a bijection, okay? And then the third property is called the transitive property. Transitive property. This one says that if we have that A is related to B and B is related to C, guess what? Well, A is related or equivalent to C. Okay, here this boils down to the fact that the composition of bijections is a bijection. Okay, composition of bijections is a bijection. All right. So this is the definition of equivalence relation. Okay, it must satisfy these three properties. Now, let's see some examples here. Here the point is with finite sets, it's very clear if two sets have the same elements. For example, I could have the set A of colors that is red, blue, green, yellow. The set of numbers 1, 2, 3, 4, and a set of fruits, whoops, that has apple, watermelon, and orange. Okay, so in this case, clearly A and B are equivalent because they have the same number of elements. Okay, we can decide to match red, blue, green, and yellow. Here it's your choice. You can just map each color to a number. Okay. But for example, A is not equivalent to C. You see, because A has 4 elements and C has 3 elements. So there is no bijection between them. Remember, a bijection has to be 1 to 1 and onto. In this case, because we have 4 elements and then 3, it may be onto but not 1 to 1. Okay, so it won't work. And then again, also it's clear that B is also not equivalent to C for the same reason. Okay, so with this type of sets that are finite, it's very easy to know if they have the same number of elements. Okay, but actually this gives us an idea of how to define finite. What is a finite set? So a finite a set is a set A such that, okay, A is equivalent to a set that we call in the book Jn, that is defined as the natural numbers that are less or equal than n. So 1, 2, 3, and so on until n. Okay, for some n. So what are we saying here? We are saying that we can consider all the sets that are like 1, 2, 3, and so on until some number n, and try all of them. And if a set is equivalent to one of these, then it's finite. Okay, so for example, with the set before, red, blue, green, yellow, I could try the sets J1, which is 1, J2, which is 1, 2, and so on. I will see that that J4 works. Well, actually, let me write the previous example. A is equivalent to J4, but not equivalent, for example, to J3, or not equivalent to J25, for example, okay? So this is the definition of finite set. So it's a set, this is basically a fancy way of saying that it has a number of elements that we can count, okay? But it's a set that finishes, okay? That it's not infinite. Now, speaking of infinite sets, infinite sets are of two types. Okay, infinite sets are sets that are not finite, but there are two types of these. The ones that are countable and the ones that are uncountable. What does this mean? So a set that is countable is a set that we can start counting elements, and we will eventually, better, if we have infinite time, we would eventually go through all the elements, okay? But it's an infinite set. Uncountable is if we cannot establish any rule. But you see, these things I'm saying, it's a little shaky, you know, because when you have infinite sets, even the equivalence that we have defined, like having the same number of elements, you need to be careful with that. So what is precisely a countable set? A countable set is such that it can be put in relation with the natural numbers, okay? So it's equivalent to the natural numbers. So this, in a way, it's like you can arrange the set in a way that it's like a sequence. Okay. I wanted to point out something about finite sets before I forget. That finite sets contain the empty set. Okay. This is by definition. Okay. One set that contains no elements, we can call it finite, but it's not clear. So it's given by definition. Empty set is finite.